So good morning, students. So this is Gnanasaravanan sir back again. So I'm happy to meet you all once again. So even today we are going to see another interesting experiment. So today's experiment is experiment number 8. So it is about measuring the efficiency of Class B power amplifier. So especially we are going to measure the efficiency of complementary symmetry Class B push-pull amplifier. There are two types. So one is Class B push-pull amplifier using a transformer, and another one is complementary symmetry Class B power amplifier. Right. So the agenda of today's experiment is we need to design and construct a complementary symmetry Class B power amplifier. Then we need to measure the output voltage. Finally, we need to calculate the efficiency. We'll be checking whether the efficiency coincides or at least gets in the range of what is being taught in theory. Right. So let's proceed further. So the equipment and components required are this. So we need two transistors, complement push-pull means, right? So one is SL100, another one is SK100. So SL100 is NPN transistor and SK100 is PNP transistor. Other than that, you need a resistor. So 4.7 kilo ohms. So that's for load resistance, and capacitor, two numbers. So these are coupling capacitors, one at the input and the one at the output. So other than that, you need three equipments: regulated power supply 0 to 30 volt for giving bias or VCC, then CRO 0 to 30 megahertz, and function generator 0 to 3 megahertz. Other than that, we need breadboard and wires. So these are the equipments components that we require. So we are under power amplifiers. Hope you know what is a power amplifier. So these are circuits that will amplify both voltage and as well as the current. There are many types I've told you. So based upon the operating point, it can be divided into Class A, Class B, Class AB, Class C. So C is not shown here in the load line, but it comes below the x-axis. So in last class, we saw about Class A power amplifier. So in today's class, we are going to discuss or analyze about Class B power amplifier. So this is the circuit diagram for complementary symmetry Class B power amplifier. So why it is called as complementary? Because one is NPN, the other one is PNP. Right. And why it is called as symmetry means it's like mirror. So on the left side and the right side, top and bottom, or like the mirror image. So that's why it is called as a symmetry amplifier. Right. So sometimes it's also comes called as complementary symmetry push-pull amplifier. This is because when one transistor is working, the another transistor will be off. When this transistor is working, the upper transistor will be off. So it is like when you push the door, you cannot pull. When you pull the door, you cannot push. So that's how it is. Right. So this is the circuit. It's a very simple circuit. You need to note down that you see here in this load line, the biasing is almost zero. So that's what here, sorry, you can see that there is no separate bias going to the base. So what happens is this circuit tends to take the biasing from the input signal. It's not, there is no separate biasing given to the base. So it takes the signal from the input signal. So that's why at the output in Class B, whether it is using a transformer or it is complementary symmetry, there is one distortion which is called as crossover distortion. So which will also tend to draw it in today's agenda, right? Let's proceed further. So procedure. So it's very simple. So as usual, we will try to connect the circuit as per the circuit diagram. You'll need to set the input voltage. So here we'll be having the input voltages 2 volt, and we'll try to see the output voltage. So we'll try to tabulate the reading. So, and we need to calculate the efficiency of the amplifier. So in this experiment, there's only one reading. We don't vary the frequency. It's not a frequency response. We're directly going into measuring the efficiency. For example, in Class A, in the last experiment, we got efficiency around 9%, and theoretically it is around 25%. We are going to see what happens today. So the tabulation goes in this way. We have only one reading. So we'll note down what is the output voltage. In order to draw, you need time period also. So you'll measure what is the time period, and then you'll try to calculate the efficiency. I'll tell you what is the formula for measuring the efficiency. Right. Hope I made very crisp and things very clear. So now it's time to go and to check whether it really works. So we are going to go on and see how the circuit is going to work. Right. So let's move to the circuit. So this is the setup. So as usual, you have a function generator to generate an AC signal, and you have a regulated power supply to give VCC, and you have a CRO to view the output, right? So here is the connection. So you have two transistors. So transistor 1, SL100, and transistor 2, SK100. So there are two capacitances, coupling capacitance at the input and the output. You can see that I've taken the output where it is merged between two emitters, and collector it goes to VCC. So this is the setup. So input, you can see that we've almost kept 2 volt, so the 2.6 volt at the input, right? So randomly I've kept some 1000 hertz, for example 1 kilohertz, right? So the output, you can see that the waveform is coming. So the only thing is you can see that there is a distortion. So what we see here, for example, I try to show you this part is called as crossover distortion. This is because it takes the base is not being biased. No signal goes to the base, only to the collector, right? Base is empty. So the input signal is given. So it takes the signal from the base. So this is what they call it as crossover distortion. Got it? So now we'll proceed to how to take the reading. So taking the reading is very simple. Let me show you. So the output voltage here, we need to measure what is the output voltage. Let me check. Let me measure it for you. So it is one box, 1.2 and around 1.4. Right. So it is 1.4 into 1 volt per division. So it is 1.4 volt. Let's check the time period. Right. So the time period, let me check, show it to you. So it's almost one box into 1 millisecond. See, 1 millisecond. So number of horizontal boxes into time per division. So it is 1 into 1, it is 1 millisecond, right? Efficiency, we need to calculate. So efficiency, the formula is, note it down, pi by 4 into 1 minus V naught divided by VCC into 100. If you need to calculate it for percentage, you need to multiply it by 100. So it is pi by 4 to 1 minus 1.4 divided by 12 volt is the VCC into 100. So you get around 69.6. So this is the model graph that you need to draw. Means you need to draw it in the real graph. So the amplitude is peak to peak is 1.4 volt. So 0.7 and 0.7. And together this should be 1 millisecond. So if you want to really see how much is the crossover distortion, that also will try to take it. So it's around 0.2. So it's around 0.2 millisecond is the crossover distortion value. Let me show it to you. Crossover distortion is here, 0.2 millisecond. So that's it. So the efficiency comes around 70%. So that is the exact percentage that we need. So class A amplifier is 25% and class B is around 70%. So class B, we are getting a very good response, right? So that's all for today. Meet you on another experiment on the next class. Hope you enjoyed it. Thank you.